Okay, we're going to spend some time talking about the imaging system and how X-ray circuitry works, and how the tube actually functions in an X-ray machine, right? So I think we've talked about already, or we all kind of understand that basically an X-ray tube works a lot like a light bulb. When you flip the switch, it comes on. When you turn it off, it's not doing anything. It's not radioactive, right? It produces radiation just like how a light bulb produces radiation. And it's on the same spectrum of electromagnetic energy that we would class things like light, right? So here on this left side of our spectrum might be like visible light. This should be kind of a review. Oh my goodness, I can't draw with my finger right now, I'm sorry. Next to that might be something like UV, right? So in between the two of them there's ultraviolet, right? We can't see that form of light. Maybe some organisms can, but the human eye can't see infrared. But once we hit the energy range of UV light, we do have the ability to cause ionization. So the energy is sufficient to ionize atoms, right? That's why, like, for example, getting a sunburn can lead to things like skin cancer. It's not that the burn, for instance, was bad. It has more to do with the fact that ionizing events occurred in your skin, and those ionizing events could lead to things like DNA mutation, right? So anything above UV light, like diagnostic X-rays, so next maybe on our list is going to be X-ray, is going to, oh my goodness, I'm sorry. I forgot my stylus. It's really embarrassing. Anything, and then beyond that, we're going to have things that are like in the therapeutic range, or frankly like radioisotopes like gamma rays, right, that are super, super high powered. Now, bear in mind all this stuff on this spectrum, right, and so over here on this other weaker side of the spectrum, we might have things like microwaves. Thank you. Yeah. I'm very tired. Things like microwaves. To this point, though, ultrasound is not on this spectrum, right? The way that ultrasound functions is it needs a conductive material, right? Like skin, or I guess air or something. I guess air doesn't conduct for it, but it needs something like the patient tissue to conduct the ultrasound wave, right? So ultrasound is a totally different spectrum, but things like the magnetic field of a Tesla, of an MRI, actually are on this electromagnetic spectrum. They're just more on that microwave side. The RF waves that they use in MRI are on this spectrum also. So things like sound waves. Okay? But the stuff that we're talking about travels in a waveform, right? And so we talk about having some of the characteristics of both a wave and a particle, right? There's that. Y'all familiar with like the term wave-particle duality? It's a theory that this stuff can behave both like matter and like energy, right? But all of it's traveling at a certain speed. Who knows what that speed is? Speed of light, which is, thank you. So all of this stuff is traveling at the same speed. How do we know what its energy range is?
The wavelength?
Wavelength and frequency. So the shorter the wavelength, the higher the frequency, the more energy it has. So an X-ray photon, for example, if I have an X-ray photon that looks like this versus an X-ray photon that looks like this, which one's traveling faster? No, they're both actually traveling the same speed. They're both traveling the same speed, right? But it's a trick question, I'm sorry. But this one down here on the bottom is going to be the higher energy photon, right? So that's more or less preliminary information, right? That when we turn on this tube, it is going to produce X-ray photons across a spectrum of energies. And we'll talk about why there's a spectrum and all that kind of stuff. But in general, if we go into a diagnostic imaging suite, we're going to have an operating console, a high voltage generator, and then the X-ray tube. Those are the basic components that you need to operate an X-ray machine. Generally, the operating console is going to be separated from the area where the X-ray tube is positioned by some kind of secondary barrier. And that secondary barrier is designed to stop, attenuate enough scatter radiation to where whatever's reaching the operator is below a significant value. It's below natural background radiation, right? And then I can point out the high voltage generator in the honeymoon suite. We can get into the X-ray room. I can show you all where some of this stuff is situated, and then the tube itself. Now I mentioned that when we're making X-rays, basically what we're doing is making a spectrum of energies. One way to think about it is you're making rainbows, right? Well, rainbow farts and unicorn farts and all that all day long. If you could put on a special goggles, right, and see what's coming out of the X-ray tube, it would be like one of those really awesome 1960s music videos with rainbows flying out of everything, right?
Like an acid trip.
Yeah, like a really awesome acid trip is the way an X-ray tube functions. Not at all. Yeah, I did not say that. No, but what it is, the significant thing is it's producing a spectrum of energies. So what we have is a kVp, a kilovolt peak, right? If that's the way you need to remember it, like an acid trip, that's fine with me. Whatever you got to do to remember that what we're talking about is a spectrum of energies. So I can tell it the maximum amount that I want it to give. That's why I have a kVp, a kilovolt peak. But it's going to give me spectrums of energy all below that. It's going to give me everything up to that. It can't go higher than that when I turn on the X-ray tube, but it'll give me a spectrum of energies, hopefully at least reaching that kilovolt peak. Right? Now, we talk about in X-ray, one thing that I think is helpful in kind of unpacking this material is to think about the ALARA concept. Who knows what the ALARA concept is?
As low as reasonably achievable.
And what's the techniques that we use to achieve ALARA? Time, distance, and shielding. The same kind of thing is what goes into an X-ray circuit, right? So I already talked about shielding. We're going to have shielding between the operator console and the X-ray tube, right? The distance factor, we will talk about some when we talk about the circuitry, but primarily what we're going to be talking about today is time, right? So you can see I have an MA selection and a time selection. And between the two of these things, I'm going to come up with a simple algebraic expression that I'm going to call MAS, mass, milliampere seconds, right? So this is an amount of time that I'm going to charge something up with an amount of energy, right? So you'll notice I've got kilovolt up here and milliamps down here, right? Put that in the back of your mind. File that away because that's a big part of what we're unpacking when we unpack the circuitry of an X-ray tube. I need something that produces kilovolts and then a separate circuit that produces milliamps. Okay? So you can see that tracks with what I see here. The kilovolt section is going to go to a step-up transformer. Right? We're going to step it up to the kilovolt range. The MA and time selection is going to be largely controlled by what we call a step-down transformer. Step down. Because I'm stepping it down to milliamps. And that's what's going to heat the filament circuit. Right? So we're going to have two separate circuits. They are series circuits, but they're operating in parallel. Okay? Here's what that looks like. Kind of drawn out in fancy circuitry notation, and I don't want you to be freaked out by this, but this is a helpful graphic in that it shows, so up here I've got the kVp section, and down here I've got the MA section. You'll notice I did not write the MAS section, so we'll talk about why that is, and we'll draw this thing out. But the big thing I want you to get from this picture at this point in time is that this section up here goes through the auto transformer to a timing thing, so there's where our time comes in, right? To a step-up transformer right here. This is a step-up transformer, and it's going to power this section right here. What do we call that section right there?
Anode.
The anode. It's going to give the anode a positive charge, right, of a certain range of energy. The MA thing is going to go through the line compensator to a step-down transformer. Here's that step-down transformer. And it's going to power the cathode. So this is going to be the negatively charged part. So this is going to be positive, this is going to be negative over here. Okay? We'll come back to this in a moment. So here are the sections of the control console. All right? It has a line monitor. That's like so that if a raccoon throws itself into a power transformer outside of the hospital and blows up the power transformer, it makes a little boom. You know what I mean? At the hospital, all the lights kind of flicker when the raccoon does that. We have a line monitor that's just making sure that that ripple in the power to the X-ray tube does not actually blow out the circuitry, right? And that's also one of the reasons we have this auto transformers. We want a nice line of energy that's coming into this thing. Okay? So that's this. All of this section here is really just designed to make sure that if raccoons blow themselves up, it's not blowing out my X-ray tube. Okay? Then we're going to have the ability to select a KVP and a time and an MA, right? So those are just selection dials, and we can go into that X-ray room. I can show you how those selection dials work, but it's just like, I don't know, selecting a volume on the stereo or something like that. Then we have a high voltage side and a filament circuit side. So this high voltage side is again the KVP side. It'll be on the top on most of our illustrations of this, and it has that step-up transformer because we're stepping it up to a high voltage. And then we have the filament circuit, and it's going to contain that step-down transformer because we're changing things to MA, milliamps, to heat up the filament. And the way these filaments work, I mean, basically what we're talking about is a space-age toaster oven, right? When you push down the button on your toaster and the filaments start to glow, that's exactly what's happening inside the X-ray tube. It's exactly what's happening inside the X-ray tube. When your toaster filaments are glowing, they're doing what's called thermionic emission. They're emitting electrons and heat, primarily heat. They're boiling off electrons, and that's making heat energy. If I had a toaster oven in outer space to where there's a vacuum, and I turned it on, and I was able to positively charge any kind of heavy metal, I would be producing X-rays, right? The reaction needs to occur inside of a vacuum. Okay, so we'll look at an X-ray tube, and I'll show you what part of it is inside the vacuum. Now, bear in mind that when I talk about how there's this crazy rainbow of energies that we're talking about, we are trying to minimize that rainbow as much as possible. We don't want a really crazy rainbow being made. And so that's what we talk about when we talk about rectifying the power to the X-ray tube. We are going to need to flip it over a series of conversions so that it doesn't ripple too much. The more it ripples, the bigger and the crazier that rainbow is going to be, right? So if we have a single phase X-ray tube, just recognize that if any single phase, which I was just talking to Tom Wolfe, he thinks that old machine that we've got is actually a single phase X-ray tube. That means it has a 100% ripple. What does that mean? I don't really have room on this slide, so I'll write it on the whiteboard. In America, we use alternating current, right? And I'm not exactly sure how this would work in Europe or what have you. But I know for sure that when we're talking about alternating current, I am applying a form of electricity to this X-ray tube that's oscillating like this, right? That's alternating current. Versus direct current, it would just be like a line. I need to convert this to something like this, right? And so the way I'm going to do that is I'm going to rectify it. I'm going to cut off the negative part of it and flip it over the axis so that I get something like this. And this would be a single phase rectification. Now you'll notice when it says 100% ripple, it's talking about you're going from 0 to, like, let's say it's 100, right? So 100%, you're going, when you turn this thing on, it's going 0, 100, 0, 100, 0, 100, 0, 100. And you're getting energy levels at every possible range of energy between those, the trough and the peak, right? So we're going to call that 100% ripple. That's not really a good thing, right? Because I told it I wanted 100, but I'm getting everything from 0 to 100. So we want to minimize that as much as possible. So we will rectify it. We have a circuitry of diodes that we're going to run the power through on the kilovolt side. And it's going to flip it once, and then it's going to flip it again and flip it again. So what we get is something like this, right? When I turn it on, it's going to power up and then hit a point where it starts to rectify itself up at the top level, right? And so now I have a ripple. If I'm talking about a three-phase, and we won't get into the pulse part of it, but if I'm talking about just a three-phase machine, I'm talking about a 13% ripple. Much, much better than 100%, right? Much, much better in terms of the energy of the X-rays that are being produced. So here again is an illustration of that. You can see where we had to, if there's a half wave, then I just had to saw off the negative part of the alternating current, but I was not able to flip it over the axis. If I'm able to full wave rectify it, then I now flip it over the axis, right? Then if I do this three-phase 6-pulse rectification, I flip it over the axis like 3 times, basically, right? And then high frequency, which is what we have in what we call the presidential suite, the bigger X-ray machine has a high frequency. It's got like a less than 1% ripple in it. So when it comes time to make an X-ray, we're going to prefer the high phase room for a number of reasons. Number one, it's going to get us better pictures, and it's going to be a less of a dose to the patient. Because if you can imagine with all this ripple, I can't control that. It's some of the rippling effects of the X-ray machine are just contributing to patient dose without actually giving me a better image. Right? I'm going to have to actually increase my time. I'm going to have to increase my exposure to compensate for that ripple. Finally, one thing that'd be worth considering when we talk just about the X-ray tube and how an X-ray room functions is an automatic exposure control. And there's a number of different ways that we can do this, like photodiode versus an ion chamber. And that means that I'm no longer talking about what happens inside of the X-ray tube. I'm talking about what happens to the remnant beam as it exits the patient. And a similar process happens within the CT machine, that it will pass through some kind of ionization chamber or some kind of sensor that says, it feeds back to this and says, okay, you can stop now. You've reached an adequate exposure, it'll cut the machine off for you. So most of what our X-ray techs are setting now is just an MA, and then they're setting a cutoff amount in the automatic exposure control. So when the automatic exposure control has adequate exposure, it's going to cut it off, right? I'm going to let time sit out here as a variable depending on when it reaches that cutoff point, okay? A similar process can happen inside of our CT machine, but just bear in mind I am talking about something separate from the X-ray circuitry right now. I'm talking about something that happens after the X-ray tube has fired off a beam of X-rays, and the X-rays have attenuated within the patient and are now exiting the patient.